Today we're going to do a review for exam 3 on chapter 8, chemical composition. And that means there'll be an exam next Thursday. For those who come in person, you can take a paper exam. If you're online, you just need to log into Blackboard through Respondus Lockdown Monitor. And anytime before midnight, it'll be counted as on time. Let's see, what else? Don't think of anything. How many burning issues that need to be dealt with from you guys? If not, let me get my paper out and we'll start review. Here it is. All right. So stop me at any time if a problem doesn't make sense or the solution to the problem doesn't make sense, or something comes to mind. You think of something that has bothered you, but it just finally popped in. I'm going to go through these. I've got several picked out, and I'm going to go through them in such a way that I don't repeat myself, because the review document, you probably noticed, has lots of repetition. So I'm just going to go through problems that introduce new topics or new approaches to solutions. All right. As luck would have it, the first 5 problems on that first page we're going to look at individually. The number of grams in 2.58 moles of sodium carbonate. Number 1. So what I like to do is extract information from the word problem. This is a short word problem, right? Some of them get bigger, and this technique works better. All right, it's more important to solving very wordy word problems. But get in the habit of doing this, and I'm going to take, what's the question? The number of grams of sodium carbonate. So we need to know how to write sodium carbonate. If you can't write the formula for sodium carbonate, then you cannot solve this problem. We know it has sodium, and we know it has carbonate. The carbonate, you won't find it on the periodic table, because it's a polyatomic ion. And the review document and the useful information in the folder with the exam will have that table. So what you do is, if you haven't already done this before, you go in through your normal browser into the folder that has the exam, and you print off a copy of useful information. If you don't already have it, if you've got the review document, then you can look at the useful information at the back of that document, but you should tear it loose from the review document and put the review document away. Just keep the useful information, or you can print it off from that folder. Then you go back out and start your lockdown browser and go into the exam from there. Otherwise, you can't take it that way. Okay, sodium carbonate. How do we balance that compound? Well, we know that sodium is an alkali metal with a +1 charge. And carbonate is an polyatomic ion with a 2- charge. Right? Which means we need 2 of those. So now we have our sodium carbonate. Let's see. Let me get everybody in attendance here. And, okay. All right. So once you've got it balanced, you don't need the charges. And we're also told that we have 2.58 moles. That's where we're at. And the question is, how many grams is that? So that's where we're headed. This is one of those cases where after you've done some of the chemistry, the rest of it is dimensional analysis. It's just conversion factor. So how do we go from here to there? You need a conversion factor that will cancel moles. This is in the numerator, denominator, and leave you with grams, right? Anytime you see grams and moles as a quotient, think molar mass. So what's the molar mass of sodium carbonate? You need 2 sodiums, which is 23.00. 2 of them. And this is grams per mole of the sodium. And then the carbonate has 1 carbon and 3 oxygens. Okay. So you just add those up. I'm going to use my calculator. Sometimes I need to use my calculator. My brain's not working really good that day. So 2 times 23 is 46. 12.01 for carbon and 48 for, plus. And then 3 times 16, add that together, 106.01. And this is grams per mole of the compound. So when you have the molar mass looks like a conversion factor to me because this many grams equals that many moles. You just have to decide, do you need the grams on top or the grams on the bottom? We need the grams on the top. Like that. So now you just multiply this times that. And I get 274, rounded off to 3 decimal points. Okay? Right here. All righty. We're off to a roll. That's number 1. Number 2. 8.52 grams of water contains how many molecules? So here we have another conversion factor problem, only this one's going to require a chain the conversion, several conversion factors together. So we're given 2.58 grams of water. Okay. And if you do this enough, you just remember the molar mass of water is 18.02 grams per mole. If you don't remember, just add up 2 hydrogens and 1 oxygen and you'll get there. So this is where we're starting. And we want to end up with molecules of water. Right? There's no conversion factor that'll go straight from grams to molecules. First, you've got to convert it to numbers of molecules. This is mass. So that's why we need the molar mass. We need grams on the bottom in this case, right? So you just put that on the bottom, right? It's a conversion factor. Remember, all conversion factors are equal to 1. So if you have a quotient, something divided by something that you know is equal to 1, then just flip it. It's still equal to 1. So that gives us the number of moles. Now we can convert moles to molecules. What conversion factor does that? Avogadro's number. All right. So now that's the thinking part. The rest is crunching numbers. 2.58 divided by 1802 times Avogadro's number. And I get, let's see, 3 significant figures, 8.62. Times 10 to the 22nd. Where is it? Did I write that right? Oh, no, I wrote that wrong. Oh, my dyslexia is kicking in. And nobody said anything. You guys are as bad as my NC classes. Just let me jammer on, make my mistakes. It's a good thing you're muted so I don't hear your giggles. Let's try that again. 8.52. $285. 285 times 10 to the 23rd molecules. Now we're talking. Here you go. That's number 2. Number 3. How many moles of aluminum oxide? Right, that's what that is. Right? Which type compound is that? Aluminum is a fixed charge. Metal, non-metal, fixed charge, it's got to be a type 1. So all you have to do is say aluminum oxide. That's it. How many moles of aluminum oxide are present in 78.8 grams of the compound? I had to check myself this time. 78.8 grams. Okay. How many moles? So if you're going from grams to moles, we do know conversion factor for that. All we have to do is add up 2 aluminum, 26.98 for aluminum, and then 3 oxygens. I get 101.96. 101.96 grams per mole. So now we can convert this. Grams on the bottom, moles on the top, so we can cancel our grams. And that means 101.96 on the bottom. And we just divide that number into 78.8. And I get 0.7, 3 significant figures. 0.773. 0.773 moles. There it is right there. All right, so let me scroll down to the next couple. There we go. Look at number 4. We're going to do all 5 on the first page on this one. Which of the following compounds has the greatest percent by mass of oxygen? All right, if you got to find out something, if the question requires investigating every possibility, then the best approach here is Henry Ford. Set up an assembly line. So I'm going to move over here a little bit, give myself plenty of room. A, B, C, D, and E. In this case, you still have to write the compounds. So it's potassium carbonate. It's like sodium carbonate, only with potassium. That's a 2 minus, that's plus 1. Okay, potassium carbonate. Nitric acid. Ic is derived from 8. Nitrate, as an acid, becomes nitric. So you need your hydrogen and you need your nitrate. This is a -1, that's a +1. So you only need 1 hydrogen. C, zinc 2 oxide, type 2 compound. We know that the charge on zinc is 2+, and it's bound with oxygen, which is 2-. So 1 and 1 is all you need. Okay, we don't need the charges now. Sulfur dioxide. What type of compound is that? Type 3. Non-metal, non-metal. So it tells you exactly how many of each element is in the compound. 1 sulfur and 2 oxygens. There you go. And the last one is also a type 3. Diphosphorus. Pentoxide. Okay, so now we have our compounds written. Next, we go back to the question, which of the following compounds has the greatest percent by mass of oxygen? So how do you do percent by mass? You take the mass of the oxygen and divide it by the mass of the compound. How do you know how much to do? Well, you have to assume that it's just 1 mole of each. That makes it simple. 1 mole of this weighs how much? We know how to calculate that. Right? So 1 mole of that weighs what? 2 potassiums. 39.10. Is 78.20. And 1 carbon is 12.01. Add that in. And 3 oxygens is 48. Oxygen is what we're after, isn't it? So oxygen goes up here. And on the bottom, we added in the oxygen is 90.21. Let me check my work again. 39.1 times 2, and then carbon, and then I knew I made a mistake. 138.21. That just didn't look right. Okay. Always be checking yourself as you go along if you can remember to do it. Otherwise, you make some of those mistakes that I show that I do. N times 100. Okay, let's set them all up first. This is our assembly line. 3 oxygens here is another 48. And then 48 plus nitrogen, look it up, it's 14.01. And then hydrogen is 1.01. So the total is 63.02 times 100. Zinc oxide. Zinc is a lot heavier. 65.38. 65.38. And then oxygen is 16. So we have 1 oxygen. And we have 81.38 on the bottom. Sulfur dioxide, how much is sulfur? 32.07. 32.07. And then 2 oxygens is 32. 6407. And 2 oxygens is 32. And lastly, 2 phosphorus, 30.97 times 2. That's phosphorus. And then 5 oxygens, 80. Yep. So 80 for oxygen. And then the total is 141.94. Okay. So we got our assembly line set up. We just need to crunch the numbers. 48, 138.21. 34 point. Well, there's no limitation to the number of significant figures, so just use as many as you want. Besides, we're comparing the percent by mass, right? So it's a comparison. It doesn't matter how many significant figures you have in these answers. I'll just pick 2. 34.73%. Oxygen. How about this one? 48 enter, 63.02, 76.17. Okay, 16 divided by 81.38 is 19.66. And 32, and 64.07. It's about half. 49.95% oxygen. And the last one. I get 56.36. There you go. Now, which one has the greatest percent of mass? Oxygen. This one right here. Okay. I know it takes a long time to do that type of problem, but if you set it up like this, you're less likely to make mistakes because you're going to do the same operation over and over and over again. So you'll need scratch paper for that one. Okay, number 5. Number 5 is a brain teaser. We're not even given real elements for our compounds. This compound with 2 X's and 1 Y has been determined to be 60% in X. It wants you to calculate the percent Y by mass of the compound X2, Y2. Okay, so let's pull that stuff out and put it on the board. Compound X2Y, X2Y has 60% X. Okay? How much Y does it have? 100 minus 60, correct? It has 40% X. Okay? How about the other compound? X2Y2. X2Y2. And they want to know what's the percent by mass of Y. All right. Remember, percent is a dimensionless number. If you're told that it's percent by mass, then that gives you some information, right? What that says is for every 100 grams of this compound, 60 grams of it is X. So why don't we just say, all right, I've got 100 grams. So in 100 grams, actually this one, you have 60 grams of X and 40 grams of Y. Okay? Well, let's take that amount and say, all right, if you have two X's equal to 60 grams, that's X, then what's the mass of Y? The mass of Y would be 80 because there are two of them, correct? We're maintaining the proportionality. So if that's true, then the total is 140 and the percent Y is 80 divided by 140. Which is 57%. So there you are right there. Okay? Now let's see, we're going to page 2. See which ones I've got marked there. Nope, nothing on page 2. Must be duplicates. Page 3, number 12. There we go. What's the mass of 5.826 moles of calcium hydroxide? Now this is similar to ones we've done before with a twist. This compound is given to you, which is nice. We didn't make you write the compound. Calcium hydroxide. The trick here is to understand how to write or how to sum the molar mass for this compound. Right. You have one calcium, 4008. Right. How many oxygens do you have? 2. How many hydrogens? 2. Right. So that is the molar mass of this compound. And I get 74.10 grams per mole. And we even need that information. Well, yeah, we're given 5.826 moles, and we want to know the mass. 5.826 moles. We want to convert that to grams. So that means this goes on top. 5.826 times that number is 43. 4 significant figures, 43.17. Okay. Did I do that right? No, I didn't. I only moved it 1 decimal. Does that make sense? Yeah. 5, almost 6 times 7 would be 320. 57 times 50 would be 3. Yeah. That's where the decimal needs to go, right there. Right here. Okay. Next one I have marked 13. Choose the pair of compounds with the same empirical formula. This one should go really quick. What's required for the empirical formula? Well, first of all, if you're going to compare two empirical formulas, you've got to have the same elements in each one. Right? Do we have any that disobey? This one's got a hydrogen here and no hydrogen there. So those can't be. It doesn't work. How about this one? Well, there's a hydrogen and no hydrogen here. So that was thrown out too. This one has potassium, chromium, oxygen. Okay, we can leave that one for now. Carbon, hydrogen, hydrogen, oxygen. Okay. So now what you do is you take the one that is apparently the largest one and try to reduce it. In other words, say we have let's do this one. How about this one? If I had that compound, then in order to write the empirical formula, I need a divisor that will go into each one equally. So let's see, 6 won't go into both of them. How about 5? No. 4? No. 3? No. 2. 2 will go into both. If I divide 2 into each one, then I get C3H7. That's the empirical formula of this compound. So let's see if any of those match. If we divide, see this one looks like it's a bigger one. Divide that by 2, you get HO. So A can't be it. We take this one, what can we divide that one by? Well, we can divide it by 6 and make CH, but that's not this one. How about if we divide it by 3? That makes 2 and 2. That's 1 right there. Right? And if you look down at this one, you can't divide that one you can't make it any smaller because that's an odd number and that's an even number. There's no more divisors that'll work. So we found our answer right here. That's B. Okay, what's next? 16. See, can I get there easily? Yep, there's 16. Calculate the number of molecules in 0.000400 grams of gaseous oxygen. Okay. Be sure you read the question carefully here. What do we have? We've got molecules of gaseous oxygen. What does that mean? It means that oxygen is diatomic. Okay, and we have, well, let's see. The number of molecules. Okay. Let's go ahead and convert this to scientific notation. All right, 1, 2, 3, 4. So that's how many grams of oxygen. How do we convert it to molecules of oxygen? Well, we got to convert mass to numbers first. The only conversion factor we have at our disposal is molar mass. So what's the molar mass of gaseous oxygen? 16 times 2. Right. So that gets rid of grams. Now we can convert moles to molecules. Let's see. 6.022 times 10 to the 23rd. Now we just need our calculator. All right, divide by 32 and multiply by Avogadro's number. And I get two significant figures. 7.53 times 10 to the 18th molecules right here. All right. Next one on my list. Turn the page. 22. Oh, too far. Let's back it up. Here we go. Acetylene gas is 92.3% carbon, 7.7% hydrogen, and its molar mass is 26 grams per mole. What's the molecular formula? All right, that's the question. We're headed for molecular formula. Is there a direct route? No. What do you have to do first? You've got to determine the empirical formula first, and then use that with this bit of information here, molar mass, to do the final step to find out what the molecular formula is. So let's do the first step, the empirical formula. 92.3% carbon. So carbon is 92.3% in acetylene and 7.7% hydrogen. Okay. Where's the problem? Those are dimensionless numbers. There's no way to convert them as they are. But if you understand what percent means in reference to a compound, percent by mass, that's 92.3 grams per 100 grams of compound. So let's just assume we have 100 grams of compound. Right? That means we have 92.3 grams and 7.7 grams. Now we're ready to go. This is the ratio by mass of hydrogen to carbon in acetylene. The law of definite proportions, espoused by Joseph Proust, says that that ratio is fixed for that compound. So we already have the ratio. That's true ratio by mass. We just need to convert this to moles and that to moles. So then we would have the molar ratio. Why would we want to do that? Because compounds are written as numbers of atoms ratio to one another, not by mass. So this has to be converted to moles. And Henry Ford is our best friend. Right, 1.01 grams per mole for hydrogen, right on the bottom. So it'll cancel here. And this is 12.01 for carbon. Right, cancel grams. Right. We're not going to chain conversions for this one because we need to know the mole ratio right now. So 92.3 divided by 12.01 is 5.19 moles. And this one is 7.7 divided by 1.01 is 7.62 moles. Let me check myself. 92.3. Let me do that again. For some reason, it just doesn't look right. No, I knew that was wrong. This is 7.69. Okay. When we get to this level, estimations are valid. What we would normally do is divide through by the smallest one. Well, what are you instantly going to see? That's so close to that one, it might as well be 1. So the ratio is 1 to 1, carbon to hydrogen. That's the empirical formula. So what are we looking for to find the molecular formula? Well, we're going backwards. Remember earlier we divided by a certain amount. Now we need to find a multiplier to bring the empirical back up to the molecular. Whatever that number is, propagates through this compound and multiplies by each of the subscripts. Okay? So how do we do that? Well, we know what this is, the molecular. We know that its weight is 26 grams per mole. What is this one inside here? Right, 12.01 plus 1.01. 13.02, correct? 12.01 and 1.01. Right? So, what's the difference here? Well, this one has had a multiplier applied to it. This one has not. So that multiplier, a whole number, multiplied by this, will give you that. So what is that number? You just ratio the two masses. Divide this one by 13.02, and it's approximately 2. So X is 2. That means our compound is C2H2. Right there. Okay? Let's see, that was 22. Let me get on time, coming up on 9 o'clock. 22, 24. Go to the next page. There it is. The molar mass of ammonium phosphate. Okay. Here we have a compound with 2 polyatomic ions, ammonium and phosphate. So you just need to look in your, if you don't already know it, look in your list of polyatomics and find those. So ammonium is NH4 plus. And phosphate is PO4 3 minus. Okay? So now all you have to do is balance the charges. But with polyatomics, you can't change the subscripts. That charge belongs to this entire unit. So if you need 3 of them to make a 3 plus, right? 3 plus, 3 minus, they cancel now. Then you have to use parentheses. Then you calculate the molar mass. So the molar mass is 3 nitrogens, right? 12 hydrogens, 1 phosphorus, and 4 oxygens. All right. Now it's number crunching time. And the last one. 64. 149.12. Okay. All right, here's an example of, you don't find that number exactly in here. But there are no other choices. That's it. You can't choose anything else but those. So the best answer is this one right here. 49.09. That's the closest. So in a multiple choice test, pick the best answer. If you don't find one that's exactly what you think it should be, pick the best one. All right, that was 24. Let's see, skip a page, let's see what's next. There must be a lot of repetition. I'm skipping several pages. Uh, 63. Let's see if I can hit 63 in the lottery here. There it is, 63. All right. Let's see what 63 has got for us. A certain compound has an empirical formula. Okay. So the empirical formula has already been calculated for it. Its molar mass is between 55 and 65. What's the molecular formula? Right? You do have enough information here. That's not a valid answer. You don't have to know exactly what the molecular formula is. In this case, you just need to know that NH2O needs a multiplier. Right? So you say, all right, what is it multiplying by? The empirical weight, or the molar mass of that formula. So that's 14.01 for nitrogen, 2.02 for hydrogen, because there are two of them, and then 16 for oxygen. Right? 3, 0, 8, let's see, 12, and 3, 3203. So this one is 32.03 grams per mole. And we're told that the actual molar mass is between 55 and 65. So is that between 55 and 65? No, it's not. What if we double it? Make this 2 instead of 1. That would be, if x equals 2, then we have 64.06 grams per mole. 64. That's between 55 and 65. So we got our answer. If we multiply this times that, we get N2H4O2. Right here. Okay? All right, let's see, 60, that was 63. We'll skip a few more pages. 83. Let's go down to 83. Oops, too far. There it is, 83. You have 12.6 grams of an unknown substance, A. So we have 12.6 grams of A. And 35 grams of chlorine gas. And 35 grams, 0.0 grams of chlorine gas. Chlorine is diatomic. Substance A contains 1.5 times as many molecules as chlorine gas. What's the identity of A? All right, you have 12 grams of A, and you know how much of this you have. So if substance A has 101.5 times as many molecules as this one, what's the identity of A? All right, how are you going to tell what A is? An unknown substance A. Let's look. What can we determine from these values? 35 grams of chlorine. We can determine the number of molecules. Actually, we don't have to determine the number of molecules. We just need the number of, which we can use any units we want. So I think we ought to use moles. Moles is numbers. So let's say, how many moles of this do we have? That's our starting point. So what's the molar mass of chlorine? Well, it's 2 times 3545. Right? There's 10, there's 9, there's 10 again, there's 70. 70.9. Divided into 35. So I get 0.494. Get this out of the way. Okay, so that's how many moles of chlorine gas we have. Now we go back to this relationship. The substance A contains 1.5 times as many molecules. So the number of moles here is what? 0.494 times 1.5. Which is 0.74, 0.740. That's how many moles of A. Okay? So we've got grams of A, we got moles of A. What can we do with that information? We can calculate molar mass, right? Grams per mole. So the molar mass of A is 12.6 grams divided by 0.740 moles. And that's 17.02 grams per mole. Right. Now we have something we can work with. But in order to figure out which one is which, we've got to determine the molar mass of each one of these compounds. So now we're back to Henry Ford. So let's put this out here, 17.02 grams per mole, and make room for the rest of the calculations. Let's see. We've got A through E. A, B, C, D, E. A is uranium hexafluoride, oxygen, NH3, ammonia, boron trifluoride, and carbon monoxide. Okay. So we don't necessarily have to calculate the exact molar mass. We can do process of elimination. How much does uranium weigh? It's 92. No, that's the atomic number. 238. So the molar mass here is 238 grams per mole. If uranium is that much, it's never going to be the right one there. So that's out. What's 2 oxygens? 16 times 2 is 32. Right? That's wrong. Okay. Ammonium is 14.01 plus 3.03, which is, let's see, work backwards. 4, 0, 3, 17. 1704. That's the one right there. If you want to confirm it, right? Fluorine is about 19 each. So 3 times 19 is 57. Right? 57. That was never going to get there. Carbon is 12. Oxygen 16. So that's 28. That was never going to get there. So we just confirmed that this is the only possibility. C has to be the answer. Okay? All right, that was 83. '91. Yeah, I need to scroll a little bit. There we go. 91. A compound is composed of element X and hydrogen. Right, so we have. So which way do we go? Well, we don't know. X and hydrogen. Could be the other way around. Analysis shows that the compound to be 80% X by mass. So this one is 80% mass, or X. 3 times as many hydrogen atoms as X atoms. So it would be actually XH3. Okay? Which element is element X? What do we need to know to determine an element? To find an element? Well, if you got the atomic number of protons, it's simple. We just look on the periodic table. That's a unique number. But we don't have access to that here anywhere. There's no way to find the number of protons from this information. So the next best thing is molar mass. If you can find the molar mass of an element, then you can usually identify it from the periodic table also. There are only a couple of places in the periodic table where the molar masses of elements are so close that you need a tiebreaker. So let's try it anyway and see if we come up with something. Okay, 3 times as many hydrogen. Which element is X? So we're looking for molar mass. We need to know grams per mole of X. All right, we got percent here. Right, so it makes you wonder. If this is 80% by mass, suppose we have 100 grams. Right? We got to get mass out of here somehow. And 80% is a dimensionless number. So if we say 100 grams, then 80 grams of X, and what does that leave for hydrogen? 20 grams, right? So we've got 20 grams of hydrogen. Okay, now we're talking. 20 grams of hydrogen is what? Well, we can determine the number of moles of hydrogen. Right? 20 divided by 1.01 is 19.80 moles of hydrogen. Okay, what's the ratio? The ratio in this compound is for every 3 moles of hydrogen, you have 1 mole of X. So we can use that to convert this moles of hydrogen to moles of X. So we need the ratio of moles of hydrogens to moles of X. And that's 3 of these for every one of those, correct? 3 to 1. So we just divide that number by 3. 6.6. 6.6 moles of X. All right, do we have everything we need? We got moles of X, and this is how much that moles weighs. So yeah, grams per mole. 80 grams per 6.6 moles is equal to what? Let's divide that into 80. 12.12 grams per mole. Now, if you go to your periodic table, you notice that from top to bottom, left to right, the masses, the molar masses increase. So you just follow along, skip period, period, left to right, until you find something that's close to 12.12. And if you look on your periodic table, the only one that fits is carbon. Right? So what does that say? That says that the element has to be carbon. CH3. Now that's not a very common compound. Carbon, I don't even know what to call it. I know CH4 is methane, but this one is, well, it doesn't say whether it's an ion, it just says it's a compound. So arguing about it doesn't make any sense. This is just a problem, right? It may not even be real, but that's the solution to it. '91. So the whole key to that problem was finding the molar mass of the element. If you know the molar mass, then you can identify it. Let's see what's next. Take my time here. Okay, I think we're going to make it. That was 91. Let's see, skip down to, well, is that the last one? Oh, there's a page stuck together. That's the last one I have marked, because the rest of them are repetitive, but we can work on any one you want. Okay, does anybody have any questions that have cropped up in the while I've been jabbering on here? That's going to finish this really early if you don't have any questions.